Okay, so first let's recall what we have done last time. Last time we started with chapter 4, but some applications of the differentiation. The first one is about the max and the minimal values. And to find the max and the mean, we also introduce the critical point. Let's recall what is the critical point. So for a function defined on a domain, then one point, so we use C for this critical. So it's a critical point. There are two cases. Either the derivative at C doesn't exist, or the derivative is 0. Okay. In these two cases, either the derivative does not exist, or the derivative is 0. We call this point a critical point. Later we will see this critical point, they are very important if we want to graph the function properly. And we can reformulate the Fermat's theorem. And let me check with you. Have you seen this name before? What's that? Okay, what about you, Skinner? Okay, before that. Uh, okay. Skinner, put your phone on the table. Your phone on the desk. Okay, just in case. Okay. Sophia, have you seen this before? This Fermat?
No.
No. Okay. So, so this a good theorem of Fermat's last theorem. It's a very big deal, maybe 20 years ago. Oh no, 30 years ago. The Fermat's last theorem, very famous. Okay, that was solved 90 about this time by Andrew Wiles. But this Fermat, I forgot. I should check. It means a few hundred years ago. Okay. So his theorem, if we reformulate using the new notation, the critical point, we can see that if f is local max or a local mean at C. Local max, local mean is something. If we draw a picture, so this point locally is a maximum, but globally there are bigger ones, not the absolute max, but the local max. Similarly, this one, a local mean. At this point, as some of you have observed, has no slope. Obviously, the slope is 0. A special case, is it possible at some critical point, the derivative doesn't exist? Okay, so again, do you have an example? Uh-huh. Huh? Okay, Sophia, do you have an example where the derivative doesn't exist?
Absolute value that.
Okay, so if a straight line, if it's this, the slope is 0. Here, slope is positive. Slope always exists. So so the derivative, so the Sophia mentioned is this. Well, this is the difference. Oh, let's switch this function. If we graph the absolute value, we see a sharp corner over there. Whenever we have a sharp corner, the derivative doesn't exist. X 0 and does not exist. And so this was the local max, local mean. The absolute max, okay, so this, for the previous example, the absolute max is over there, absolute mean over there. So mark that point. So steps to find the absolute max, absolute mean. Okay, from the definition, we have to compare the value at each point. There are too many points. We cannot do that. So what we do is we find the values at the endpoints. That's easy, just two endpoints. Then in the interior, we find the critical point and compare the values of this critical point with the endpoints. So how to find this absolute max minimum? So, critical point. We solve the equation. Then we the points and at critical points. Now we have a finite collection of points. Endpoints, 2 points. Critical points, a few when we solve the equation, or when the derivative doesn't exist. We can compare the values at a much smaller collection. Previously, we have to check that one by one. Okay, which one is largest, which one is smallest. Now we'll only check a few points. That's the application of this. Okay. And the next section, we prove a very important theorem. The mean value theorem. So to prove this mean value theorem, we started with a special case, the Rolle's theorem. This is the special case. It's like under the assumption that f is continuous. And differentiable on recall that we see a function is continuous on an interval if it's continuous at every point in this interval. It's a differentiable on the interval if it's different, has a derivative at every point on the interval. Are you, Alice, are you familiar with this, Zichen? continuous on interval. Okay, so when it's not continuous? If there's a jump, if there is something crazy oscillation, or when there is something, we change the value over there. So when we say it's continuous, you think, okay, what's not continuous? Then that doesn't happen. Similarly, when we say it's differentiable, what do you have in your mind? Okay, so if we say differentiable, think about the opposite. When it's not differentiable. If it's not a continuous, then it's not differentiable. Similarly, for this one, at this point, there's no derivative. It's also not differentiable. So give it a statement. Think about the complement. When it's not continuous, when it's not differentiable, that doesn't happen. Okay, so about the differential, continuous differentiable, then we have another assumption. F A equals F B. The conclusion is at some point the derivative must be zero. Okay, so first, what's the condition? The condition is let me draw an interval. A B. The condition is the function is continuous on this interval. Continuous and differentiable. And the derivative and the endpoints have the same value. Then the claims we don't know what this function is, but we can find a point in the interior. Here I have two choices. We can choose this point, we can choose this point, at where the derivative is zero. The derivative. So let me mark at this point. So the theorem says as long as the two endpoints have the same value, then somewhere in between, there's a point where the derivative is zero. So if the derivative is positive everywhere, it will be increasing. It cannot go back. If it's negative everywhere, it cannot jump. So for this to have the same level, start, end, at some point, we must have a turn. The turn means the derivative is zero. Okay, so that's a special case. Then we use the special case to prove the general case. The mean value theorem. General case is, again, same condition. Another maybe feature of this statement this statement is about the existence. There must be some point. It's zero. There must be some point where the derivative equal to this. But it didn't tell us what this point is. Is it in the middle, on the left, on the right? We don't know. We cannot tell from the theorem. The theorem only guarantees there exists something. Okay, like if we drive from one place to another, 100 miles, we arrive in 1 hour. Then we can tell at some moment one is speeding, but we cannot tell it's at this moment or at that moment. We don't know, but somewhere we must be speeding. Yes, that's another possibility. We say it goes faster, slower, slower, faster. What if they go the same speed? If they go the same speed, then this point could be anyone in between. So this means if we think of this ft, the position at time t, then the f, b, f, a, the total displacement, total time, this will be the average velocity. Or the mean velocity. Okay, so what does this mean? I use the short notation because for in the future we may use this several times. It's the mean value.
No, I understand that. I'm saying the definition, like when you wrote it, like it just like I just don't know what, like I don't know.
Okay.
I just get here.
So first, what is the mean value? Mean value. So sometimes you today I make $2, tomorrow I make $4. What's the mean?
The most theorem to explain that. What it's proven, like what is the mean value theorem?
Okay, sure. Okay, so let me finish this. I'm going to draw. Let me draw a picture. What is this? That's a very good point. Let's see what it tells us. At A, at B time, we start here, we arrived there. I don't know what happened in between. We may go faster, then slower. That's possible. Okay, now if I consider the this quotient, the difference over the time, this will be the slope, that's the mean velocity. Okay, let me draw a line. Could I draw dashed line? I'm not sure. Dash, oh, perfect. Okay, give me 1 second, let me finish this one. And then we'll go back to that one. Okay. You mean this?
Yeah, I don't know that.
Okay, so this means if I write this in word, I will say and C, E, A, B, a number in this interval.
So there's a number in the interval
Uh.
where the derivative is happening.
Yes. Yes.
So I just did that.
Okay, cool. Okay, so I can go a little bit further. I can even say A less than C less than B. So there are many different ways to interpret, to say this. C is a number in the interval, or C that's bigger than A, that's less than D, less than B. Okay. Now, so suppose this is our situation. Can you tell me where the point should be, where the derivative is the mean velocity? So Could you find a point in this interval where the derivative equals the mean velocity? Could we go here?
I don't know.
Okay, so let's pick. Okay, if I pick, does this work? Okay. If I pick this point, Zichen, what do you say about the slope at this point? Compare with this one. Which one? So, okay, yeah. If we pick this point, the slope is higher than average. Now, if I move, let's pick this point. What's the slope of this point? So Sophia, no, Sophia, Sakina. So if we compare this slope with the mean slope, right? That's the key point. So we will check over here it's bigger, over here is smaller. How do we find a point where it's equal? Oh, yeah, so we just try. Okay, it's too big, we go over there, it's a little bit smaller. Maybe go over there. So as the point moves, the slope becomes smaller and smaller and smaller. At some point, it must equal to this. Okay, so that's how to find this. So this is the slope. I moved over there. All right, this point. Okay, let me switch to. Okay, about it. I can use the dot plus. Let's put this. Okay. By trying and error, I find if I start here, slope is too large. If I start here, it's too late, slope is too small. Somewhere in between, we have the exact slope. At this point, we say at this point, the instant velocity equal to the average velocity.
I learned this.
Okay, so now if in math, if we start here, the derivative is too large. If we start from here, the derivative is too small compared to this one. At this moment, the derivative is exactly the slope. So the theorem doesn't tell you where it is. The theorem tells you there must be some point. Because from too large to too small, tells me if we move from too large to small, at some moment is about right. That's the mean value theorem. Uh, if we go consider a different situation, if we go from there, then too small to too large, then at some moment it must be right. Okay, so not a very difficult theorem. Just see the graph. Just say, okay, okay. Yeah, so that's a very good way to learn mathematics. Between formulas and the graphs, formulas is very precise, but the graph is very intuitive. You should go from formulas to graphs, and from graphs back to formulas, back and forth. Okay. And Sophia, what do you think?
I think that it will be the parallel
Okay, yeah.
spot where like it's parallel
Mm-hmm.
to like the mean line
Mm-hmm.
and
Yes.
It will only touch on one point, so it'll be like the tangent.
So for this case, there's only one point at where the tangent line is parallel to this displacement line. When the two lines are parallel, they have the same slope. If we consider a different example, so someone, they travel at a different pattern. They try a different one. They move quite differently. Okay, a different function. Now the same thing. I'm going to find the mean slope. Okay, let's start with Zichen. Could you give me a point where the tangent is parallel to this one? You mean over there? Okay, so we have one. I'm going to try to draw this a nice way. Okay, it's about right. We have 1 point. And Sakina, could you give me a second point where we have the same slope as this? Okay, it's somewhere over there. It's about, okay. Oh, let me redraw this. A little bit off. And Sophia, another point. There's third point where we have the same slope as this line over there.
It's
Okay, you draw it. I saw it. Okay, I
yeah.
saw it. Okay, so you draw it over there. Let me recreate your drawing. It will be somewhere over there. Okay. Now for this function, we found 3 moments where the instant, or where see the slope of the tangent line equal the slope of this total displacement. Now we can see the theorem tells us there exists someone, but there could be exactly one or more than one. Okay, the guarantee the existence. Okay, so let's have one interesting application. One interesting application of the mean value theorem. Let's consider a function. We suppose it's differentiable, and we know the derivative is 0 for every x. What can you say about this function? If the derivative is 0 everywhere. Okay. Okay, Sophia, what do you say?
It's a line. It's a horizontal line.
Okay, so the graph of this function must be a horizontal line. Or we say it's a constant function.
Mm.
It's a constant function. Okay. How do you prove this? Why? The derivative is 0. Why it must be constant? Okay, so let me draw a picture, then we can work on it. A, B. Okay, so that's FA. If at some point the value is different, it may be higher, maybe smaller. Let's assume if at some point it's bigger. Okay, what happened? Could we get a contradiction from this? Could we? So we wanted to prove it must be constant. So we will prove by contradiction. If it's not constant, if somewhere the value is bigger, we will derive a contradiction. Okay, now let me check with you. Have you seen this term before? Contradiction. What does that mean? Contradiction. Okay, okay. So Kina, what do you see contradiction? Okay, and Sophia, what's your explanation for contradiction?
It's like the opposite.
Okay, okay. It's you all get the idea. It's an inconsistent. It's like the okay. Some of you know that this in Chinese. Do you know this in Chinese? Do you know? Okay. Sophia, what about you?
No,
Okay, now you do know this. The Chinese translation of this is Mao Dun, the spear and the shield guy. Okay, so it's about the so it are inconsistent. We want to derive a contradiction from this assumption. If we have this, then we want to get a contradiction. It's inconsistent. To do this, we will apply our mean value theorem. Okay, so we know the value is different, then there must be some point at where the slope is equal to this. Then it's not a 0. Okay, so contradiction. So let me finish the proof. If at some point is bigger than by the mean value theorem, we can find C. In the interval with derivative equal to the mean slope fd minus fa d minus a. So the numerator is positive, denominator positive, then this will be positive. So this contradicts the assumption that derivative is 0 everywhere.
So it's like,
So let's see how we prove this. We prove that if the conclusion is false, the conclusion is C everywhere. We say if this is false, we get a contradiction. So it means this must be true. If this fails, we will have a contradiction. Okay, so let me repeat. This is what we wanted to prove. Okay, now we will assume the opposite of this. The opposite, this is the opposite. These two are incompatible. If we assume this, we get a non-zero derivative. Then this is the contradict the condition.
So does it prove it? No.
Yes, prove it. Okay, so the logic here, we want to go from this way. So we take a detour, we say, what's the opposite of this? The opposite of this is, at some points, it's different. If the value changes, the derivative will be non-zero. We get a contradiction. Okay. Okay, maybe we will come back to this later, but at the moment we will see if the derivative is zero, f, yes, this is right. That's right. Okay. If the derivative is zero, there must be constant. Okay, so we will deal with this proof thing later. Okay. Okay, so now graph, let's learn more about graphing. Okay, first, very simple observation. If the derivative is positive, what can we say about the trend of the function? It's the same, the bigger or smaller? Bigger, okay, so that's good enough. If the derivative is positive, the f is increasing. If the derivative is zero, okay, then what do you say about the function? It must be decreasing. Okay, Sophia, if the derivative is zero, what can I say about the graphing? It's increasing, decreasing, or the same?
That means that the graph is the same.
Okay, so in this case, it's possible it's increasing. It's possible it's decreasing. It's possible it's the same. We cannot tell. So in this time, I have to say inconclusive.
Oh yeah, because it's just linear.
Oh, wait. Top. The top.
Okay, so let me show you. So here the point is at this single point, not everywhere. If it's zero everywhere, okay, we have just proved it's constant. But at a single point, we cannot tell. The example okay, you said okay, examples. Okay, so I will make it more precise. The cubic function, x cubed. X cubed. At this point, the derivative is zero. So fx even though the derivative is zero, the function is still increasing, just very slowly. Okay, that's the first one. Now let's see what happens when the derivative change signs. They change it from positive to negative. What happens? So if the derivative changes from positive to negative, what happens on the graph? Okay, so it's increasing, then decreasing. So there's a critical point and the local maximum. Okay, that's a good observation. If the derivative changes, from positive to negative at C. So FC is 0 and C is local maximum. The graph looks like this. Similarly, if it changes from negative to positive, at a point, then the opposite happens. Before C is decreasing, negative. After C is positive, so that's the local minima. Okay. Now let's go a little bit further. If we have this graph, so this is fx, we will compare the derivatives of this function at a different point. Let's pick 2 points. For clarity, okay, Sakina, let's compare the derivative at these 2 points. What do you say about the derivatives? Different, bigger or smaller? From here to there. It becomes smaller. So if the derivative becomes smaller, what can we say about the second derivative? If the derivative decrease. Okay, think about this. So let's go to the previous one. If the function is increasing, the derivative is positive. Function decreasing, derivative negative. The derivative decreasing, what do you say about the second derivative? No. No. Okay, let's see. If the function increasing, the derivative is positive. What's that happens to the second derivative about the derivative? So the second derivative is the derivative of this one. So if we copy the story over there, for this to decreasing, the derivative is negative. The derivative of this is negative. So the conclusion is, okay, let's compare with another picture. Another picture where the derivative is increasing. See what's the difference? Okay, another 2 points. Sophia, what do you say about these 2 derivatives? What's that?
The
Uh-huh.
derivative of that is going to be
Same? Increasing or decreasing?
Increasing.
Okay, so this time f increase. Then what do you say about the second derivative?
It would be linear.
Okay, so this time the second derivative will be positive.
Mm.
Okay, so how the derivative changes? This one, the derivative becomes smaller and smaller. The second derivative is negative. The derivative becomes larger and larger. The derivative is increasing. Second derivative is positive. So you can see this will give us two different shapes of the graph. This way, and go to this way. So we have a different term for this because it's concave downward. Terms is concave upward. Let's see. Let's think about this function. Y equals exponential x. Let's recall what's the graph of this function. If I graph it, it will be something like this. Oh, no, not this. Let's check the derivative of this graph. It becomes bigger and bigger. In particular, in this one, the derivative is, okay, Zicheng, what's the derivative? E to the x. What's the second derivative? Okay, now we can see because the second derivative is positive, the derivative is increasing, and the function is concave upward. Okay, so the logic, we go from the second derivative is positive, the derivative is increasing. And the function is concave upward. Okay, so from we have more and more properties about this graph. Initially, we say, okay, the function is positive. Okay, that's not good, that's good enough. With the derivative, we can say the function is increasing. Now with the second derivative, you can see a little bit more. Not only the increasing, it's increasing at a faster speed, faster rate, concave upward. So if we go with the logarithm is not exact. Oops, too bad. So logarithm is increasing, but increasing at a slower rate. It's concave downward, concave upward, to complete different behaviors of this. Okay, maybe let's have a break to 55, and after that we will do something more interesting. Okay, have a break. Okay, so let's skip a few details. Sophia, are you back? Sophia? Okay. Uh, and move to the next interesting topic, 4.4. Indeterminate. Okay, now I'm going to check with you. Okay, Jen, have you seen this guy before? This L'Hopital? You haven't? And Sophia, what about you? Sophia, I
I've heard
cannot
of
see your
it.
face. Okay, maybe adjust your camera.
I've heard of it.
Okay, so uh, so this guy, I think it's French. So the spelling is a little bit different. In some book, you see hospital law. In some book, they put a cap on this O, omitted the S. So how to pronounce this guy? It's l'hôpital, because in French, they often silent H. So if you call this guy, it's called l'hôpital.
It means the hospital in French.
Okay, so not law hospital, there's no S and there's no H. L'hôpital is a French name. Okay, so what is in indeterminate form? Indeterminate form is comparison limit goes to 1. Okay, let's think about this for a minute. How do you find this limit? Could we plug in y? Denominator cannot be 0. So for this one, when x goes to 1, both numerator and denominator, they go to 0. We cannot plug in. Could we simplify, like factorization or cancellation? Could we do that? Okay, so here we cannot plug in. And we cannot simplify. Okay, so the L'Hopital rule allow us to find this limit using a very useful formula. Okay, so we call this an indeterminate form. I keep going the wrong. Indeterminate. Determinate. Okay, I keep in. So this is indeterminate. There's actual R over there. How do I correct this? Indeterminate. And in the sequence, we will introduce quite a few different types of indeterminate forms. So we will give a special name for this type. This type, the numerator and denominator, they both go to 0. So we call this the type. So again, be careful. This is not a fraction. we didn't put a 0 on the numerator, 0 on the denominator. It's not a number, it's a type. Okay, keep in mind, we use this not as a number, not as a fraction, but as a type. It's one type of this indeterminate form. It means we cannot substitute x by 1. And we have something like this before. Let's try to recall that. What's the limit? Okay, both of you, what's the limit? Okay, she said 1. Do you agree or not? Yes, that's correct. This is 1. At that time, we use the geometric argument. We use some trig functions, and over there we use some quant analysis. We find this limit. So here we will give a second approach using L'Hopital's rule. Okay, what is L'Hopital's rule? L'Hopital's rule is for this form only. Okay. Let me copy the L'Hopital's rule. Be very careful when this rule applies and when it's not applicable. They both go to 0. Then we assume it's all differentiable. Both. Then the limit. Okay, so we cannot plug in, but we can do something about it. Be very careful about this statement of the theorem. The limit of the quotient equals to the limit of the quotient of derivative. Let's compare this. Is this the derivative of the quotient? Okay, yes or no? So if we take a derivative of this, do we get this one? No, we should have the quotient rule. So here it's be very careful. This is not the quotient rule. In particular, there's no reason we apply quotient rule. Here, they are very different. We will give a quick proof of this, but before that, let's first check whether it's correct or not. Let's apply it to this one. Apply L'Hopital's rule to this limit and see if you get 1 or not. Okay, let's check. Check limit. Okay, but by L'Hopital's rule, I will use LHR. L'Hopital's rule. Limit A 0. Okay, Zichen, what's the derivative of the numerator? Cosine x. And Sakina, derivative of the denominator. 1. Sophia, what's this limit?
It's negative Wait. Oh, it's like 1.
Cosine 0. So that now we can plug in. You see, it's very simple. You compare to what we have done in the previous sections to find this limit. We go this triangle, this circle arc, we quite some proof. But if we allow us with this L'Hopital rule, we apply the derivative, then we can plug in. Okay, so this one seems to be complicated. We have no idea how to do that. Let's apply L'Hopital rule. Find. Okay, this time let's start with Skinner. What's the derivative of the numerator? What's the derivative of this? Do you remember this, Zichen? Logarithm. Sophia, what about you?
1/x.
Okay, Sophia, remember this is 1 over x. Okay, so Zichen, derivative of the denominator. One. And Sakina, what's the limit? All right, okay. You see, very difficult limit. We cannot plug in, cannot simplify. There's no other way we can do. We have to use this L'Hopital rule from a very complicated one to a much simpler one. Okay, another one I think we have found. Let's check that one. Limit x equal to 0. We did this before. Cosine x minus 1 over x. Okay, do this on your notebook. So how to find this limit? Let's try. Do you get the same limit as we had before, or you get a different one?
So
Okay, sure. Yeah. No worries. I just worked around. Check your process. Okay, but let's recall maybe a few weeks ago, what was that limit we found? 0. That's correct. Okay, so limit by L'Hopital rule to be the derivative negative sine x minus 0, 1. Now we can plug in. Okay, so now, so this seems work, but why? Let's consider a case when the differentiable and both exist and g, this is not 0. Okay, under this assumption, what is this? F, okay, proof of L'Hopital limit. We will assume the limit is okay. So what's the definition of the derivative at A, Sakina? It's the limit of something. Okay, yes. And Zichen, what's the definition of a G derivative? Yes, yes. Okay, now even you don't remember, but you saw that, you say, okay, it's the same thing. Okay, that's good enough. You use what you have. Okay, there are two definitions. We could use XA, or we use A plus H over H. Okay, two versions of this. They both works. Okay, since we assumed both limits exist, this is a very important step. Okay, I'll get all your attention to this. We assumed both limits exist, then the quotient of the limit equals to the limit of the quotient. Okay, very important. So if we, let me put a star over there, limit. Okay, Sakina, Zichen, and Sophia, this step is not trivial. This step is, be very careful about this step. What's the difference between these two? What's the difference? Uh-huh. Yes, that's the very big difference. This one is the quotient of two limits. We take a limit first, then we take the quotient. This one we take the quotient and one limit. Okay, very important. We have now, okay, we simplify. Okay, Zizhen, how do you simplify this? Okay, then we get fx minus fa gx minus ga. Okay, now let's ask ourselves, is the type, okay, over there, 0, 0? It means both go to 0 when x equals a. So f, a, g, a, they're all 0, right? So let's plug in, they're all 0, we have since fa equals ga is 0. Okay, now let's compare where we started and where we finished. This is what the L'Hopital rule claimed. That's two had the same limit. So keep in mind, this is a proof of a special case, but it contains the main idea. So I emphasize the limit equals this limit. So the limit of the quotient of functions under this assumption is an indeterminate type of 0 over 0. We have this. So that is the condition. If both are 0, we can apply L'Hopital rule. Okay, that's a very good point. Let me give you, let me see where that is. I want to find something. Okay, let's try another one. Limit x go to 0. It's similar to what we have done before, but I moved the ones. Okay, let's find this limit. Okay. Okay, if we plug in, see what we get. Plug in cosine 0, 1 minus 0, 1 over 1 is 1. If we apply L'Hopital's rule, see what we get. L'Hopital's rule. Okay, let's also try that. If we apply L'Hopital, limit x go to 0. Okay, Zichen, derivative of cosine, negative sine. Sakina, numerator, the denominator. Okay, minus sine, minus cosine. So they cancel each other. And Sophia, could we, what's next, Sophia?
It's now you plug in.
Okay. So we can plug in, or so we can simplify the either way. So this will be 0 over 1 is 0, or it's tangent x, tangent 0 is 0. Okay, now we have two different answers. 1, 0. So what is this limit? 1. Okay, why is this incorrect? Okay. That's a very good point. So here we have to be careful, because when we learned this, L'Hopital is very powerful, but it get misused, maybe abused. So this is an example where it's not applicable, because this is not indeterminate type, not the type. Because if we find the limit of the numerator, we get 1. Limit of the denominator, we get 1. It's not our type, so we cannot apply the theorem. Okay, so essentially, this L'Hopital theorem tells us which one go to 0 faster. Okay, which one go to 0 faster? Fx go to 0, gx go to 0, limit. So to check who is faster, we can go to the limit of the derivative. Okay, let's have some simple ones. Limit x go to 0, tangent x Okay, let's try to find this limit. Okay. Could we plug in? The first question. No, okay, it's because the numerator, denominator, they all go to 0. Now it's the type 0/0. Okay, type. We can apply L'Hopital's rule. Now we need to think. Derivative of a tangent. Sophia, derivative of a tangent x. Do you remember that one?
Secant squared x.
Secant square x. And derivative of x, we all know is 1. So now it's limit of x go to 0. Secant x. Secant. What is secant 0? What is secant? Sine or cosine? Okay, yes. So it's 1 over cosine. 1 over 1 squared is 1. Okay, so this limit is also 1. Okay, now we are going to try something more challenging. Limit x go to 0, x minus sine x over x cubed. Sophia, could we plug in 0?
No.
No, okay, so that's the first step. Always check if we can plug in. This again, denominator goes to 0, numerator goes to 0. So the type, let's use a different color to emphasize the type. Okay, so let's move on to L'Hopital's rule. Let me know when you finish the first step. Sakina, derivative of numerator, what do you have? Okay, so derivative of this, what's derivative of x? Derivative of sine x. Okay, so it's 1 minus cosine x. And the Zichen, denominator. Now you see very quick. Okay, so last time I checked, you see not sure. Now you are very sure with good x squared. Okay, Sophia, could we plug in?
No.
No, because if we plug in 1 minus 1, 0, 0 against is yes, because it's the type. It has the type, so we can apply. So we do the derivative again. Okay, Zichen, derivative of a numerator. Sine x. Sakina, denominator. 6x. Sophia, could we plug in?
No.
No, why?
Because sine 0 is 0 and
Mhm.
6 times 0 is 0.
Again, type 0, 0. Zichen, what should we do? Again, okay, let's do it again. Do we plug in this time? Okay, eventually we get something that we can plug in 1 over 6. So you can see sometime we have to do this multiple rounds, but each time we have to check we have the correct type before we decide to go ahead. If we go ahead like we have for this one, get something incorrect. Okay, so we are, because we are people, we are very smart. We know what's correct, what's wrong. Should be careful, and we'll have more about this next time. Let me stop recording. And any questions? Okay, next time.